분야는 것처럼 더스트입니다. 그렇지만 더스트만 하는 게 아니고 더스트를 가지고서 여러 가지 응용 분야 CMD라든지 그리고 최근에는 이제 인터스텔라 트래블 앤 엑스플로레이션이라고 해서 이렇게 스페이스십이 날아가면은 더스트가 어떻게 들어가는 그런 재미있는 일도 이렇게 했습니다. 황 박사는 최근 아주 연구적이 우수합니다. 지금까지 약 한 100편의 SCI 논문을 발표했고
인정에서 그다음에 H-index가 32 정도쯤 됩니다. 그걸 스칼라 기준. 사실 논문을 많이 발표하고 인덱스 이렇게 높지만 저는 개인적으로 출연을 얼마나 많이 쓰느냐라고 하는 것이 상당히 중요하다고 봅니다. 황 박사는 지난 5년간 한 60편 정도 논문을 발표했습니다. 그러니까 1년에 한 12편 정도 평균 논문을 발표했죠. 그 중에 반 정도가 주저자. 그래서 제가 생각할 때는 황 박사는 지금 이제 한국 국내에 있는 천문학자 중에서 가장 연구가 연구적이 이렇게 뛰어난 활발하게 연구를 수행하고 있는 연구자라고 이렇게 생각합니다. 근데 이제 사실 학자로서 연구자로서 이렇게 논문을 많이 쓰는 것도 중요하지만 저는 개인적으로 그 외에 커뮤니티에 얼마나 기여를 하느냐 그리고 그 분야에서 리더십을 어떻게 연구 분야에서 리더십을 어떤 식으로 이렇게 발휘하느냐라고 하는 이런 것들도 중요하다고 봅니다. 황 박사는 최근에 국적이 베트남 있지만 한국과 베트남 사이에 천문학 교류에 대해서 교류를 활발하게 진행을 하고 있습니다. 예를 들면 최근에는 미국의 사이먼 파운데이션이라고 하는 곳에서 지원을 해서 사이먼 베트남의 퀴논에 있는 연구소에 사이먼 아스트로피직스 그룹이라고 하는 것이 만들어졌습니다. 여기에서 황 박사가 이걸 만드는 데 상당히 주도적인 역할을 했고 이 프로그램을 통해서 베트남과 한국, 베트남 연구자를 한국으로 이렇게 리크루트해갖고 이런 작업을 하는 건 사실 내가 예를 들어 한 가지인데 그 외에 여러 가지 활발한 활동들을 많이 하고 있습니다. 제가 생각할 때는 황 박사는 지금 이번에 수상한 한술상의 가장 정확한 연구자가 아닌가 이렇게 생각을 드립니다. 황 박사를 다 박수로서 환영해 주길 바랍니다.
안녕하세요. 저는 팀입니다. So first of all, I would like to thank you very much for coming today. And especially I would like to thank the organizers for inviting me. And I really like to thank Professor Dong Soo Ryu for a very nice introduction. Although I don't understand Korean, but I can guess his meaning. Okay. So it's my great pleasure for being here, especially after more than 2 years of COVID. I think okay. So if you allow, thank you very much. It's much more convenient. So I remember the last time I gave the talk in person at the meeting, in-person meeting. It was just the beginning of the COVID pandemic in Vietnam. Where we organized the conference with Professor Ryu and yeah, this way. Okay. Yeah. So the conference, the last conference in person we organized in Vietnam is on magnetic fields in the universe. So I'm very happy to see all of you in person here. So today I'm going to talk about new frontiers in dust astrophysics. Dust is quite familiar to all of you because in our daily life, we always want to get rid of dust. But I think one of the advantages of working on dust is that you can touch it and you can feel it. In astrophysics, I think we cannot get away from dust because we don't have any tools to remove dust to get clean signal. So we have to live together with dust. And it seems that when we decided to live together with dust, we make dust very interesting. So my talk will be focused on dust, but because in addition to dust, radiation and magnetic fields are also ubiquitous. So astronomers will work with radiation, and magnetic fields are everywhere. So the interplay between dust, radiation, and magnetic fields is the foundation of modern astronomy. So you can see here the interplay of dust and magnetic fields have a very huge impact on other research areas, including star formation, planet formation, and even the emergence of life. Even if you want to understand the beginning of the universe, you have to work with dust. You have to remove dust, actually. So this is the outline of my talk. So first, I will show you a very brief introduction about why dust matters. Why do we care about dust, and why dust is very important. Then I will move on to talk about the fundamental physics of dust, astrophysics. So about the interaction of dust and radiation first. And this is the foundation of the astronomy, optical, infrared, and millimeter astronomy. Radiation has three fundamental properties: energy, momentum, and spins. So I will show you that how dust can extract these fundamental properties and make it more useful. And I will move on to talk about the integration of dust, magnetic fields, and radiation. I will focus on the how dust interact with magnetic fields, and it makes dust polarization. And that is the foundation of dust polarimetry. And we use dust polarimetry to explore the universe. And I will finish with a short summary. Okay, so here dust, you can see, you can observe when the sun is setting, and it is called the zodiacal dust, zodiacal dust. And dust is also, you can see at night, you see with your naked eyes, the dust appear like a dark patches in the sky like it. But if you use an infrared camera, you see the Milky Way looks very beautiful. And now with the arrival of the James Webb Space Telescope, we can see the universe even more beautiful. And even if you look into the universe at very long wavelengths, like a microwave with the wavelength about 1 centimeter, you still see the signature of dust. And this is the kind of emission from spinning nanodust particles. With some new emission component which was recently discovered. Okay, so now the dust emission appear to dominate the energy distribution. So this is a spectral energy distribution, and a long wavelength above the mid-infrared here, you see that dust emission dominates the whole energy spectrum, even from mid-infrared to far infrared, and then even in sublimeter here, it has AME, the thermal dust, AME. So dust emission provides very wide windows into the universe, and that why dust is important. Now, so where does dust come from? There are two main sources of dust in the universe. First, from AGB stars and red supergiant stars. The second source is from supernova. So we know that heavy elements are synthesized in the nucleus of stars. So when a star is dying, or even like when supernova is exploding, the heavy elements in the different shell of supernova are expelled into the surrounding. And when they are escaping, they cool down, and then gas, heavy elements condense to form dust. So dust from supernova and AGB star are injected into the interstellarium. And now dust begin its very interesting journey. Dust can control the star formation. And from star formation, dust have a chance to spin and form planets. And on the surface of dust grains, complex organic molecules, even water molecules, that is the emergence of life. Also play in stellar feedback, in galaxy evolution, and even it's also the puzzle for CMB study. So dust plays very important role in astrophysical processes. Now, so let me summarize the fundamental physics of dust and radiation interaction. So in the first simple case, oh, sorry, I keep moving. Here's some lag. Yeah, so in the first case, the interaction of radiation and dust, in this interaction, dust just absorbs photon energy, and then the dust is heated up, and when it is heated, it can re-emit emit energy in long wavelength radiation. But if the dust is heated to very high temperature, the thermal fluctuation energy inside the dust can exceed the binding energy of atoms or molecules, and then it results in the evaporation, or we call thermal sublimation. In the cold environments, dust grains have an ice mantle on the surface. So in the ice mantles, there's very rich chemistry. Complex organic molecules are being formed. And then under the action of protostellar radiation, complex organic molecules now can grow and even make more complex organic molecules. And then they may dissolve when the ice mantle is heated to above like 100 Kelvin. So that is the foundation of astrochemistry. Now, the dust and radiation interaction in this process, dust can also absorb photon momentum. And photons can transfer momentum to the dust grains, and then the dust grains receive some radiative force. And the radiative force now from dust can transfer to the gas through collision. And that drives the outflow, stellar outflows, galactic outflows. And here is the radiation pressure can drive the mass loss for AGU star, and even for driven for the galactic outflows. And radiation pressure is also important for stellar radiation feedback and also the formation of massive star. So radiation pressure is considered one of the barriers for the formation of very high mass star. And radiation pressure can even accelerate dust particles to relativistic speeds. So in our paper in 2015 with Alex Lazarian and Raiha Srikaiza from Bochum, we show that if dust grains are located in the vicinity of very intense radiation source like a AGN, they can be accelerated to very high speeds. This is the Lorentz factor, this is the luminosity of the source. So for some grains, like a 0.1 grain, they can be accelerated to like a 70% of light speed. So dust grains can move at relativistic speeds if they receive enough photon radiation pressure. So that is very important. So nature can create relativistic dust grains. Now, how we can learn from nature? Yeah, we can learn from nature by using photon momentum to propel our spacecraft. So that is the idea of interstellar travel using radiation pressure. And actually, the idea of using sunlight for traveling within our solar system is not new. The Japanese space agency, JAXA, already started their experiment here in 2010. And the Planetary Society also tested the light cell, the solar cell, within our solar system in 2019. And the real breakthrough came when Breakthrough Starshot Initiative was launched by the billionaire Yuri Milner and Stephen Hawking. You can see here. So the goal of Breakthrough Starshot is to visit the nearest star, nearest stellar system, named Proxima b here in 20 years. So in order to visit another stellar system in 2 decades, the spacecraft must be very tiny, like a nanocraft, and it must move at 20% of light speed. But there are many challenges, because when the spacecraft is moving at relativistic speed, they can collide with the interstellar dust. And in the rest frame of spacecraft, dust grains appear like a relativistic bombs or mini bombs. So dust in the interstellar medium can destroy the spacecraft, and that is a very good, very challenge. And so these are showing. I'm going to show you the video showing the concept of the spacecraft, relativistic spacecraft proposed by Breakthrough Starshot. So the idea is we can create a very powerful laser system similar to AGN in the universe, and then we can accelerate the spacecraft to relativistic speed. Yeah, but the challenge, as I said, the destruction by interstellar dust. And another challenge is when the spacecraft is moving into the ISM, the spacecraft gets charged through collision. And then the charged spacecraft can interact with interstellar magnetic fields, and the spacecraft gets deflected. And it doesn't go to the target, but it's deflected. And that is the real challenge. Okay, so that is a new frontier with the dust and radiation interaction. Now, let me move on to the third aspect in the dust radiation interaction. Dust grains can receive the photon spins. So we know that photons have a spin 1. So that means it has left-handed and right-handed angular momentum. So if the spherical dust grains are illuminated by left-handed photons, and the dust grain can receive some angular momentum, some spin from photons. So the dust grain can spin up. So interestingly, the Nobel Prize in Physics this year was given to the work on a pair of entangled photons. So two photons have opposite spins, and they can keep the fundamental properties even how far they are. So it's not related to my talk, but it's something related to the fundamental property of photons. Okay, now in nature, we don't have a left-handed or right-handed photons because the natural light is unpolarized. So, So the first people who noticed this is a model how dust grains can extract photon spins is Dauggenhoff and Mitrofanov in 1976. So at the time they realized that if the dust grains are helical, like a twisted ellipsoid, and then they interact with a beam of radiation with left-handed and right-handed photons. So because the grains have a helicity, so they can absorb differently left-handed or right-handed photons. So after the absorption and also scattering, the dust grain can receive some net angular momentum, which is radiative torque. So the torque can spin up the dust grain. But that very simple model was almost ignored after 20 years until Dren and Wagner, they can quantify radiative torques for irregular grains, for more realistic irregular grains, like you can see here, with teeth shape. So they demonstrated that through electromagnetic dipole approximation calculation, they show that radiative torques are indeed very strong. And recently we can calculate radiative torques for many shapes, and we reached the same conclusion. Radiative torques are very efficient when the grain diameter is greater than the wavelength, and it drops significantly when the diameter is larger than the wavelength. So now how radiative torques can affect the grain dynamics. As we know in the grain motion, radiation pressure can accelerate dust grains to very relative speeds. So radiative torques can do the similar effect, but here they do not accelerate, but radiative torques can spin up dust grains to very fast rotation. By the way, I also would like to stress that in the model of Dauggenhoff and Mitrofanov, they rely on the photon angular momentum or photon spins for dust grains to get radiative torques. But in our model in 2007 with Alex Lazarian, we just use the photon momentum. And using photon momentum, we can also derive a radiative torques from analytical formula like this, very basic calculation. And we show that our analytical model of radiative torques can reproduce very well the calculation of torques using numerical computation simulation. Okay, so now radiative torques. One of the important property of radiative torques is that radiative torques can spin up dust grains to very fast rotation. And the rotation rate depends on the radiation intensity of the source. So if dust grains are located in the vicinity of very strong radiation source like a supernova, they can be spun up to more than 1 billion rounds per second. So within such fast spinning grains, material exposed or experience very strong centrifugal force. So centrifugal force here can exceed easily the binding energy that by different components of dust grains. So when it happens, the whole dust grain can be split apart, producing many smaller fragments like this. And this is very important effect that we discovered, and it is not expected by Edward Purcell. So Edward Purcell, who won the Nobel Prize in Canadian mathematics, he suggested that dust grains cannot be split because of centrifugal force. But at the time, he didn't understand about radiative torques. And until recently, we show that radiative torques are very efficient. Okay, so here you can see, for example, we consider a light source like a supernova, and the light curve from supernova increases rapidly, and then it goes down. We calculate the rotation rate of dust grains exposed to the supernova, and you can see the rotation rate of dust grain increase rapidly with time. The time here in days, and it can easily exceed the maximum rotation rate that the material can survive. So large grains can be disrupted here. And here is the radiation source. So depending on the location of dust to the source, dust grains located closer to the source get disrupted first. And then it now result in the space variation of grain properties. So near the source, we have a smaller grains. Far away from the source, we have a large grain. And this effect can help us to explain some puzzles with the research on supernova. So many observations towards type 1a supernova, they show that the extinction curve towards supernova and gamma ray bursts are very steep in UV. That means the parameter that characterizes the grain size, RV, is small, and we don't know why. Here we show more details. For example, for many supernova, dust properties have the RV about 1.7, much smaller than the value from Milky Way dust. That means the grains in this vicinity are smaller. And before our explanation, there was no any convincing explanation why dust are small. And we calculated the RV, the extinction towards supernova, and the grain size are modified by radiation from supernova itself. And we found that initially grains are just large, and then they have a typical value about 3.1 RV. And then as soon as the radiation disruption happens, the RV decreased rapidly from 3.1 to smaller value. So these values are consistent with the observation from supernova. And now, what is the new frontier for cosmic transient and time domain? So for cosmic transient and time domain astronomy, usually we want to study the variation of the light curve, colors, and reddening, so that we can use the properties to infer more fundamental properties like a Hubble constant. But all the studies assume that the dust, foreground dust, have constant properties. But with our new effect here, we show that the radiation from cosmic transient can rapidly modify the properties of foreground dust. So in order to accurately characterize the property of cosmic transient, we have to model carefully how the dust properties are changing because of the stellar feedback. And this is very something very challenging. Now, let me move on to the second part of my talk, is about the interaction of dust, magnetic fields, and radiation. Why do we care about magnetic fields? I think magnetic fields are everywhere, even in our room here. And in the universe, magnetic fields are present almost everywhere as well, from the sun, planetary system, Milky Way, extra galaxy, and even around black holes. So dust and magnetic fields are both ubiquitous, and they always interact with each other. Because if dust grains have a charge, they can interact with magnetic fields. But we are not talking about the interaction of charge and magnetic fields. We are talking about the interaction of how spinning dust can interact with magnetic fields. So in order for dust grains to interact with magnetic fields, they must have a magnetic moments. So basically, the magnetic moments are the key parameter that help the dust grain to couple with magnetic fields. And This related to the composition of dust. We know that iron is one of very abundant element in the universe, and observations show that more than 90% of iron should be in the dust. So if iron is locked in the dust in this form, the dust become paramagnetic material. So paramagnetic material, that means it has some unpaired electron spins or unpaired magnetic moments. So if atoms are present in the form of nanoparticles embedded in the dust, like this cookie. So this black seed is one iron nanoparticles. So now each iron nanoparticle behaves like a giant magnet. And then it has a magnet like this. So these dust grains are spinning because of radiative torque or because of collision. So when the dust grains are spinning, all electron spins light up. So initially, if the grain is at rest, all electron spin have random orientation because of thermal fluctuation. So we have a net zero magnetic moment. But if the dust grain is spinning, the transfer of macroscopic angular momentum to microscopic angular momentum and make all electrons spin light up. So this is a magnet effect, which is inverse effect from Einstein-de-Haas effect. So it shows the relation between macroscopic angular momentum and microscopic spin. So when the spinning dust grains have a magnetic moment, now the dust grain can interact with magnetic field, and the magnetic torque is M cross B. So this magnetic torque helps the dust grain to preset the magnetic field B. That is called a Larmor precession. But radiation also plays a very important effect in this game. So for example, if we have ambient magnetic field B, and the grain is spinning with angular momentum J, and it has a magnetic moment mu, so the grain is precessing around magnetic field B. Now, because we have radiation, the radiation, we know that create radiative torques on the dust grain, and radiative torques can spin up the dust grains. For example, the component of radiative torque along J can spin up the dust grain, but radiative torques also have a component which is perpendicular to J, and this component change the angle between angular momentum and magnetic field. And then it can bring the angular momentum to be aligned with magnetic field B. And this is called alignment of dust grains with magnetic field B. And eventually, all grains are rotating with the long axis perpendicular to magnetic field B. So systematically, all grains will be aligned with magnetic field B. And we demonstrated the effect through numerical simulation. So we consider how the grain orientation changed under the effect of radiative torques and magnetic fields. And we show that indeed, initially all grains have random orientation. The angle called psi here, psi is the angle between J and B. So initially all grains have random orientation here. But because of radiative torques, grains can be driven to this attractor point and this attractor point. So this attractor point has a high angular momentum than the thermal value. So we call it high J attractor, and this is a low J attractor. So the high J attractor is very stable. It is not easily to get randomized by grain collision. So we have a very efficient alignment. But grain at low J here can be easily randomized by gas collision. So eventually all grains from low J will be picked off and transported to high J, and grains become perfectly aligned. And in this alignment picture, the alignment is driven by radiative torques. But when grains have magnetic properties, we know that because of iron inclusion, the effect of magnetic relaxation or paramagnetic relaxation can enhance the alignment by radiative torques. So we show here that if grains have enhanced magnetic properties, all grains will be aligned with magnetic field B. And the alignment degree increase with the amount of iron locked in the dust. So here the x-axis show the amount of iron locked in the dust, and here the alignment degree. So you can see that the alignment degree increase with the amount of iron locked in the dust, and then it gets saturated. Okay, so one of the important implications of dust alignment is that the alignment dust grains can induce the polarization of starlight. and also it can emit the polarized emission. For example, if dust grains are aligned with magnetic field like this, the thermal emission is strongest with the electric field along the long axis. So the thermal radiation from dust have a polarization vector perpendicular to magnetic field. So if we can observe a polarization vector, we can now rotate 90 degrees and infer magnetic fields. And it is a very popular method to infer magnetic fields. Here are the magnetic fields obtained by dust polarization. For example, the magnetic field from LMC, magnetic field from the full sky by Planck, magnetic from filaments observed by JCMT and SMA, and magnetic fields observed by ALMA. So dust polarization is very powerful method to test to map magnetic fields and measure magnetic fields. And we test the alignment theory by radiative torque and alignment and also radiative torque disruption. Now radiative torque have two fundamental effects, alignment and disruption. So we test by comparing our modeling with observation. For example, from the modeling, we predict the polarization degree for different radiation field. Radiation field also can be characterized by dust temperature. So in the case of only alignment, the polarization degree should increase with radiation field, the black line here. But when we have a disruption, the polarization first increase and then it decrease. The decrease of polarization happen when the disruption happen. And we see here, the disruption happen here. And we test with the observation data from Sophie Hochglass and also from Planck. And we found very convincing evidence for the alignment and disruption by radiative torques, as you can see here. So the first test is for rho O focus A. You can see the similar behavior here. Polarization increase with dust temperature and then it goes down. We also found the similar evidence in another star forming region, LMC, 30 Doradus. The polarization increase and then it decrease. Where for M17, the polarization also increase and decrease. And we also tested whether the decrease in polarization here may be due to magnetic field fluctuation. And here we show the fluctuation degree of magnetic field with the dust temperature. And it shows no correlation at all. So the drop in polarization here is induced by the disruption effect. We also compare with Planck data. Yeah. Okay, so let me summarize the history of the grain alignment physics for 70 years. So beginning from the discovery of starlight polarization until recently, the RAD paradigm. And the RAD paradigm solved the 70-year problem of grain alignment. And it also discovered the new effect disruption, and it opens new frontiers in astrophysics. So I'm moving quickly towards the final slides. For example, we can now, using dust polarization to observe magnetic fields in unconventional environments. For example, we can observe magnetic fields in supernova ejector. Here's a result from COPA. And we found very strong magnetic fields in this environment. And the magnetic fields observed toward extragalaxies. We can also use a dust polarization to test the effect of magnetic fields on star and planet formation. The ALMA now is revolutionizing our understanding about how star form or planet form, because ALMA have a high resolution that can help us to measure magnetic fields in very small scale. So here's the result from ALMA. And so that the alignment can now produce the dust polarization that we observe with ALMA. In order to test, we need to combine our theory with observation. And it shows our working flow from theory combined with simulation, radiative transfer, and synthetic observation. And we compare with ALMA data. And then we can be sure that, okay, in the very dense environments, we still can trace magnetic fields using dust polarization, as we can show here, we can see here. Yeah, so we show the how our synthetic polarization compare with observation. So the shaded area here show the data from ALMA, and we show that our results can successfully reproduce ALMA data only when dust grains have an embedded iron cluster. So that's a very important conclusion. And we show that the polarization increased with the amount of iron. And that opened a new way for us to constrain how much iron is locked in the dust. And that can help to solve the missing iron issue in the Asia. And so with that, I'm going to skip this slide. That is very important, is related to how to understand planet formation, but I don't have enough time because Professor Liu is standing up. The dust physics now is also important for understand astrochemistry based on the rotation. So I'm skipping it. Okay, so I should skip this slide. It's very interesting, but I don't have a time now. It's also related to dust and ice.
This kind of
Yeah, so finally,
another extreme is the prolate type, and this is an
Yeah,
extreme of oblate.
just
Another question
this
is
has some lag.
about the
Sorry. Yeah, I would like to put this
quantitative
slide to
measurement
thank
of
all my
magnetic field.
collaborators,
saying
my
that
postdoctoral
the-
students
you
who
can
have
use
contributed to the
polarization,
results that I show in my
to
talk.
inform
And
magnetic field
with that,
or
I would like to
measure.
thank you very much.
So
and
measurement
take
means
question
not
now.
only the direction but also the size of the magnetic field. You never mentioned about the magnetic field size.
Yeah, thank you very much for a very important question. So my first question about grain shape. And actually, physically, we don't have any strong preference for grain shape. Given the complex nature of dust in the intermedium, I think grain shape, yeah, we don't have any clue actually. But from the inverse modeling, like when we build the model of emission and polarization and we compare with observation, it seems that nature prefers the oblate grain shape. I think back in your very classical work with Bruce Rain in 1980 something, I think in your model you prefer, you support the oblate shape. And recently, very detailed work by Bruce Rain and his student, they fit the model in both emission, polarization, and extinction. And they seem to support the oblate shape for the intermediate. And if they use a Brownian shape, the axial ratio is very extreme, and they rule out that possibility. And from the physical point of view, I think I have that idea in my mind, but I haven't written the paper yet. Because grains are spinning, so the centrifugal force tend to make dust grains to have an oblate shape rather than a Brownian shape. I was thinking about that, but maybe I need time to write that paper. Yeah, for the second question about the measurement of magnetic fields, in my talk I don't have a time to talk about how we measure magnetic fields, but basically the first step is we measure the morphology or the direction of magnetic fields by rotating 90-degree polarization of dust emission. But if we want to measure magnetic field strength, we have to use an additional method. The popular method now is based on the work by Davis, by Chandrasekhar Fermi and Davis in 1951. We call it DCF method. So the DCF method can help us to measure magnetic field strength. The idea here is the interstellar gas and dust and magnetic fields are turbulent. So the turbulent kinetic energy actually induces the fluctuation of gas. So by measuring the spectral light, we can measure the turbulent component of the velocity of gas motion. And assuming that we have an equilibrium between turbulent kinetic energy and magnetic energy, we can infer the magnetic field strength. That is the basic idea. But now we have several modifications of that method to measure the magnetic fields. In addition to dust polarization, we can measure magnetic fields using other methods like the Zeeman effect and signature radiation, Faraday equation. But as far as I know, dust polarization is the most popular method. It can measure magnetic fields in almost every environment in the intermediate. Zeeman effect cannot measure magnetic fields in very dense environment because the signal is very weak.